Jonas Sanford Institute of Neuroscience. Um, that's my main affiliation with just UCSF. I'm just a researcher there at this point. As for Han Gian, he is a PhD there, so he's a PhD under Karnish Ganguly for maybe the last 4 years. And this is what we've been working on, which is at the lab to decode signals from a paraplegic participant and control a robotic arm using these imagined movements. So that's why we're here today. We're going to present some of that work, but we just want to have a very comprehensive guide towards gesture decoding, whether that's for like muscle signals, like with the first arm we're going to present, and then or like brain signals later. And you'll see it follows a similar theme because I want to make this intimidating subject feel more approachable for people, because it's still something that's kind of unexplored by a lot of like papers. It's literature. There's a decent bit of literature on it, but towards a more feasible option, like a much more affordable option for people, there's still more work to be done. And so
Cool.
that's why we're here today. Um, okay. So, all right, let me screen share. I can screen share one thing. Oh, if the approved uh, request for.
You should be able to screen share.
All right. All right, now I have it. So, all right, do you guys, hold on, let me make sure. Can you
Yep.
guys see my screen properly? Okay. Let me see if do you guys see the Zoom windows or just the screen? Like,
Just the screen.
okay, that's good. All right, so this is fundamentals of gesture decoding and the concepts and methods by Rashab Ray and Hongyi Yang. So first of all, the worldwide context, we have approximately 22 million people with worldwide limb amputations, upper limb. These are mostly in war-torn and conflict regions, as usually that's what leads to upper limb amputations as opposed to lower limb. This number has increased since then, but unfortunately, because there's not a lot of research on this, the most recent research papers I've seen on this usually very um, have much more broad estimates on, say, general amputations as opposed to like specific types of amputations. So this is the earliest one I could get for upper limb. And this just goes to show about how there's still a little bit of lack of research in this area in order for us to help people in underprivileged regions. But to add on to that, the price of usual commercial myoelectric prostheses are range from like 4,000 to 5,000 for the minimum, and then it can go all the way to 100,000 if you would so like. Like for example, the Hero Bionics, the Open Bionics entry level arm cost about $7,000. And while you do get 2 degrees of freedom, so you can do two or three gestures with it, it's very expensive, and then it's a completely unfeasible option for people in like underprivileged regions, as well as people here, because insurance is not always going to cover it. And then the other thing is that one of the reasons they're so expensive is because they use something called high density electrode arrays. And if you can see in the corner, it's basically a muscle sensor with many more electrodes. And it gives you more surface area, but it just becomes much more expensive when creating it. So that's why I've set out to use a cheaper system as well as a more sparse electrode system. So for our hardware setup for this project, we have for our hardware setup, we have the Bitolino muscle bit system. This is available from Portugal, and we use only 4 electrodes. And we use this 3D printed modified version of the e-NABLE Phoenix hand, where we've basically extended it to have like a servo plate. And so you could have the servo motors at the back of the arm that can control the fingers towards the front. I'll be showing a picture of this later. And we use an Arduino Nano as our microcontroller, which will control the servos. As for our electrode placement, we specifically kept them on the ulnaris and radialis, these parts which flex, because they're commonly associated with the index finger flexing and as well as the last 2 fingers. The abductor polus longus is for the thumb opposition because usually thumb signals don't generate as much like muscle signal and amplitude. And so there are very specific movements one must do in order to get that get the proper signal from the thumb. And so that's why we've placed it here. So if you see the abductor, so this is a flexor carpus ulnaris, this is a radialis, this is the extensor digitoria, and then this is the abductor polus longus, which is on the bottom of your wrist, right? And we've picked this placement specifically for, better decoding. As for our EMG filters, we run a bandpass filter from 20 hertz to 400 hertz and a notch filter so that we can cut the power line frequency. Usually in US, the power line frequency is about 60 hertz, and it can interfere with the signal when you're recording. And so that's something we would like to avoid. Yeah. So now for our participants in protocol, we had three subjects and we made them do 3 sessions of recording each. And we did 10 loops of these 5 distinct hand gestures, which kind of go like this, thumb, index, and you have this control as a fist in the middle so that you are able to distinguish with these gestures and you're not confounded by like switching from this gesture to this gesture directly. And it's just a consistent control in some sense. So we just decode the activity periods as we see on the bottom here as the gestures we're trying to decode. So we usually keep the fist period shorter and the activity period longer, and we can do this loop 10 times per participant. And so we have about 30 total loops as data that we've done for this project. So one of the reasons if you can see, we did the ring and pinky extension. One of the things we face is that because these two are so kinematically similar, in order to do just the forefinger, one of our participants wasn't even able to completely flex his fourth finger without moving his fifth finger. And so we realized, okay, they're very kinematically similar, and it would be very hard to distinguish and very uncomfortable for the participant. So we decided to put them together as a gesture. As for the palm, this is like towards the end, but this is just the most common gesture that we can see for like a muscle signal that, if you wanted just one action to be done, palm or fist, then you should be able to distinguish between those two for basic functionality. For our features the characteristics we extract from the signal, we take the root mean square of the first 4 seconds of the activity. We take the root mean square is essentially you take every point, every data point, EMG data point, and you first square them, you take the mean, and then you take the root. We also take the mean absolute value, which is taking the absolute value of all the points and then taking the mean. These two are more or less redundant features, but we just want to make sure that if there was any difference, then it would be covered by having both of them here. But they perform the same action, which is try to get amplitude of your signal. The waveform length is essentially the length of the wave across whatever window you've put it. And so this is just an important thing to understand, like how long is the person's the period of the frequency which the person is recording with. This can be a useful feature. We've seen that it increases our like classification accuracy by maybe 3 or 4%, along with the zero crossing, which is in 10 microvolts, meaning that above 10 microvolts of energy, it detects if it's past zero. So like the signal has some certain vibration, which makes it past zero every few seconds. And negative to positive, if it goes above this energy threshold, then we count it as a sign change, like it's changed from this side of the axis and gone down to the bottom. And so it's also a very useful feature here. We also extract the power across 4 frequency bands. And this is the beta band, which is 13 to 30 hertz. We take a kind of low gamma band, which is like a 30 to 70 hertz, a higher gamma again to 70 to 150 hertz, and then we just go beyond to 150 to 250 hertz and 250 to 400. You may ask, well, why are these windows so big? Because they're not as specific and narrow as you'll see later on with our brain signals. And the main reason, we just want to capture certain measures of energy and amplitude. It's not so much a drifting signal or like there's some pattern you want to see in there's just different aspects of amplitude that you want to analyze with the higher frequencies. You may see more, for example, here, you'll see towards the end, so towards the beginning, you'll see it's a much lower frequency and it doesn't jitter as much, but towards the end, there's a lot of um, like discoherence almost with this, like it becomes a lot more jittery. And in order to distinguish the signal of, say, this gesture from this gesture, you would want something which can see those higher frequencies. And so that's why we have those features. We take 8 features total per channel. And so if we have 4 electrodes, this means that we would have 32 features in total for our decoder. Okay.
Question.
Yes.
Oh, so just to make sure I understand this, so each one of these bands is those different digits being exercised. So the green band is the fist, and then the darker
Yes, so
green is the
these are,
thumb,
oh
and
yeah,
then
sorry,
okay,
I didn't go over that quite. Yeah, so this is our protocol. So this is a recording of a participant's protocol. And we can see that this is the first, this would be the thumb. The second, so the black one is the fist period, the control period we have in between. You can see a very clear difference. This is the index finger for the next one, the middle finger for the third one, and this is the ring and pinky, and then this is the open palm, and it repeats. I'll be showing you 2 different blocks of these gestures from a different session for the same participant, just to show you how we were able to train it off, like train our decoder off this first session and be able to test it on another session and account for the difference in this baseline signal that we were receiving, usually like physiological variability. But yeah, sorry, I didn't explain that. So, but
thank
that's
you. No
yeah.
problem.
So now let me go next. So, all right. So these are our 2, this is just a block of the signal. And we can see that this is a cross session. So this was for the first session of our participant. This is the one that you guys saw on the other slide. And this is this same participant, but on another day. So you can see that some gestures perform, like they may have some pattern. I've plotted this as like the power envelope. So they have some similar pattern, but there's still some slight differences. And this may be due to like the participant's blood pressure or even just the way they perform the gestures. And so to account for this, what we've done is we've taken the mean and variance of the first fist period, and we've z-scored the rest of the activity periods based off this mean period so that we can basically recalibrate our signal to whatever our um, cross session is, right? Because there's some variance. And so, but there's still pretty big similarities, which is why it's still able to decode a cross session. So yeah, this is the main thing we do for accounting for a cross session. Yeah. Yeah. So now for the ARM design, so thanks to, I guess, e-NABLE, we had access to this ARM design, although it's more of a proof of concept now, is the e-NABLE Phoenix V3 arm. And then we had a servo extension that we made with some servo plates and stuff to just pull the strings. It's controlled by a microcontroller, and you would have, it would be able to control the arm for you. And this was just to show that the gestures that were predicted by our decoder, which we'll be going over a little bit later, would transfer to our arm in low latency, and it works. And so yeah, that's about it. That's how we do the gesture classification. We first have these separate gestures. We'll train on the first session of the participant. We'll test it on a separate session so that if someone, say, uses this arm and we've trained it on maybe 2 days of their data, they'll be able to use it another day or like another 2 days. We still have to do long-term testing for it, but the main thing is that with this low-cost arm, it could probably be achieved at a much more like a much lower price compared to, say, the Open Bionic and stuff, which relies on the similar technology, which is EMG systems. So yeah, so this is the total price of everything besides the sensor that we use. The Bidelino sensor costed $250 out of, and it basically took up the entire system cost. So that's what still has to be changed in the future, because I think everything else was much cheaper for this device. So yeah, and this is our PCB as well. All right. So results, we got 94% cross-session accuracy for the 3 subjects. So we would train on the first session and test on the next session for our subject. We got 94%. The worst accuracy we got per subject was about 92%. The main thing to note here is that the subject could be tired sometimes. I think it's mostly due to that variance, but I'm pretty sure in the future this accuracy could probably go to 100%. The main confounding gesture that we saw across all of them, and I think the reason is because they kinematically encompass all the other gestures, is the palm gesture. So when you do the palm gesture, you are opening your index, you're opening your 4th and 5th finger, right? And you're performing all the gestures at once. And I think sometimes it has a little bit of trouble with that. But generally speaking, it performs pretty well. And we'll be going to like the internals of like a decoder a little bit later on with the robotic arm, since they're similar in many aspects. The robotic arm itself was able to produce was able to properly execute all 150 gestures from 50 gestures from each respective participant. So, it has pretty good performance. I think down the line, if we were to go towards real-time decoding, I think something like this is more feasible if we decided to decrease the size and make it so that perhaps an amputee could use it. The last thing, though, we probably have to do in order to... Yes.
Sorry, quick question on the previous slide. You said this is 15% of the cost of the system. What's the rest? You said something, I missed it.
Yeah, so the rest is just the Bionic sensor. It's 240, like 240, 250. And yes,
okay.
so the EMG system, the electro system is probably the most expensive part of the device. 3D printing it almost costs nothing, right? Even making the PCB is extremely cheap. It's mostly the EMG. And so that's something I do want to look at down the line, so that perhaps people can open source it, especially when e-NABLE, that's something, we can make more accessible prosthetic arms down the line. But yeah, so that's probably the biggest issue that we have to face with the device. And the robotic arm was able to replay all the gestures. So as of now, it is not real time, meaning that we first have these signals sent to our gesture decoder, and then it is predicted. It gives a prediction for them, and then we send those predicted gestures to our robotic arm. So that will be something we have to implement in the future. But this is more of a proof of concept for now. So that's about it. Before I go to the next part, do you guys have some questions about the EMG stuff that I can explain?
I do. So just to get the big picture, you have a chain of custody, a workflow here, in which you have EMG sensors from a kit that costs about $250, which feeds into
like
a classification system, which is an AI
like some computer
classifier.
Right?
And the AI classifier is running on a laptop, is running on a...
It's usually running on a laptop, but in the future, we plan to integrate it on like a much smaller, like microcomputer almost. There's systems out there like the Raspberry Pis and stuff that you can basically integrate. It's a multi-layer perceptron as our decoder. But for now, we do it on a laptop because I think there are some changes that we have to make. Yeah.
And this is actually something that was relatively hard to do a few years ago, I imagine, where you were sort of hard coding filters, et cetera, in order to try to do the classification.
Right.
And those were notoriously flaky.
Right.
It sounds like the AI, like the human, is able to weed through the
Distinguish them
noise and
better.
just get the intent. Is that right?
Yes. Actually, there's something nice I can go about this here. Let me first, I can show this initially. This is something important that we can because I do think this is relevant now that you've brought it up. So one thing is, in order to distinguish these two gestures between these different sessions, right? If we used a linear classifier, meaning that we used like a threshold where we just drew a line and had a boundary, you can kind of see why sometimes this might not work, right? This signal, for example, had a completely different amplitude in the way it expressed itself, right? So how does it cannot just be off the signal's amplitude to distinguish the gesture, right? And so that's why when you go to more like complex classifiers, where you can give them the truth, you can say, okay, this part, you train it on this part of the data, you give it truth so it can constantly repredict and shift its nonlinear equation that can classify to predict better. It just gets the feedback, repeats the process, gets the feedback, and eventually it trains and trains until it gets this accuracy. And it actually does it better than most humans do. So these patterns that we see, which are visually discernible to us, it will be even more consistent because we've picked apart different parts of the signal for the computer to look at. And so it can just find correlation across, like various different things that we can't even see. So that's the advantage of using like a more special, what we call multi-layer perceptron, which is a very basic classifier that can perform nonlinear classification. And so, yeah, that's why it's necessary to go towards this way for like consistent usage. This wasn't possible before, though, right? Before people used to just do simple threshold methods.
Right.
Okay.
So
now,
after training this system,
yes,
you now have a neural network with all the appropriate weights to do a damn good job of
yes, that's the
recognizing.
idea. And yeah.
So I would imagine that the apparatus for training. So these days, the big boys train these LLMs. They train these AIs, and we use the trained system, which is running in a very different setup than the training setup. So help us translate that to here.
So one thing is, there's one thing to understand. The LLMs that people like companies use today they deal with enormous amounts of data.
Sure.
When we run a MLP, like a multi-layer perceptron, and it can be a very small like neural network. It doesn't have to be very big. It typically, it's because we're not feeding a lot of data on it. If you have a small computer, like maybe like a Raspberry Pi 02W, it's like a small version of a Raspberry Pi, probably this big, right? And you could probably train it for someone on that device. And then you could just, when you're actually trying to do real-time processing, you can save the decoder weights and then just export those to have your neural network equation in the future so that when the person does it real time, we'll send signals to it over. Well, you also
and all
see
of that
here,
is in principle doable within the Raspberry Pi. In one mode,
that is in principle. I think the
develops
equation,
the weights, and in another mode, it just retrieves the weights in order to be a good classifier. Okay, great. So then, in real time, it's not clear to me whether you've done this or not. I can make a gesture and it goes to the perceptron and it says the guy is pointing with his index finger.
Right. Yeah. And it gives you prediction. So I have not done real-time implementation for the robotic arm, but for the brain implant work that we do at UCSF, we have done real-time on it. So yeah.
And once it says pointing the index finger, you then send the appropriate signals out to the servos, and they make the
it's just
index
a
finger
gesture,
point, and that's a relatively conventional process.
Very simple thing. Yeah. So the more complex part is the gesture decoding. I would say that our ARM design could be much further improved, but it's more of a proof of concept in the decoder side of things, since I think that's something we didn't have before for so long. So yeah.
Okay. So I have a much better understanding of sort of the big picture than I did before. Other people may have questions, but I'm good if you want to proceed.
Okay. Does anyone else have questions?
Not right now.
Okay. So control robotic arm using brain implants at UCSF. So first, our setup, we have we take these continuous electrocortiography recordings. It's this brain implant, which is implanted on the top of your skull. at the surface of your cortex, so it can take signals from there. And it has 256 channels, and it is actually a high density electrode array. It has a 1,000 hertz sampling rate, meaning we take 1,000 data points every second. And this is approximately where it's positioned around the brain. And it encompasses a couple of different, it's at the top of the brain. This is more of a diagram to show how the sensor would look on top of someone. It encompasses a bunch of different motor, like the somatosensory sensory motor cortex. And what it does is usually a lot of these are associated with movement and preparations before movement. So that's why this is a place for our implant placement. We have 2 paraplegic subjects who attempt to control the robotic arm using their brain signals. This is the end goal of the project in of its own at the Ganguly lab. So yeah, this is our robotic arm. So this is our experimental protocol. It is pretty similar, but the task state is outlined much more clearly than the EMG one we had before. So we have a cue. So the participant is sitting and they have like a screen in front of them, maybe to their left, and they will get a cue from the screen, do the right thumb. So they have to prepare, and they'll prepare for maybe 4 to 5 seconds, and then they'll go for probably 4 to 5 seconds. And at this point, this is the activity that we mainly want to worry about. This is where we train our real-time decoder. We obviously, when the person's doing the activity, we feed these weights that we've already trained on a decoder before to now test it real time, right? And so it outputs a gesture decision every 200 milliseconds. And the idea is that once we decodes it, it sends it to the robotic arm so that the person can do it. When repeating this, right, in order for the participant to know that he has imagined the correct gesture, because he's not physically doing anything, he's only asked to imagine the thumb or the middle finger or like moving his left thigh with the gesture. So we have something that gives him some feedback, which is the arm in real time, which moves a certain direction based on whether he's done that gesture correctly or not. And so say in the next loops of our recording, we first have like a open loop training where we just train off the person's imagined movements. And if it classifies this correctly from the machine, because you know the truth, you know what he was supposed to do, and if the decoder did it correctly, you give it, it's going to train. But then on the closed loop part, where now the person starts getting feedback based off this trained open loop decoder, the arm will move and give him feedback so that he can further improve his inputs, maybe if he's doing it a certain way, right? So this is the protocol. It's still pretty similar. It's just much more isolated towards one gesture at a time. Okay, now for our feature extraction, we extract these features over 200 millisecond windows. So we use something called a Butterworth IIR filter, but really what this is doing is it's like a fast Fourier transform, except it's a little bit better equipped for real-time processing. It just takes less time to do and less computational power. We extract mainly 3 frequency bands from 0.5 hertz to 4 hertz, the beta band for 12 to 30 hertz, and the high gamma band. The high gamma bands have been strongly correlated with like movement execution and stuff. So when the person's actually doing the activity, this one spikes quite a lot. The beta frequencies, this is just a general thing throughout, even like the literature, are strongly associated with movement preparation. So if we look at if the period where the participant is told to prepare and wait these couple of seconds before the gesture, you'll see a very small window of time where the beta bands will show some activity just as he's about to do that gesture before his like any activity happens in the activity window. And then the delta band, this is something we've just seen which performs very, very well throughout our testing. And you have to, because of its small period, you have to calculate the delta band over a larger window. So like the power envelope over, say, this window, and then you can cut off the last 200 milliseconds. So say you were to, it's a little bit like an aggregate, like buffer, that's what we call it. So like say you were to have the power, like this is the power, the delta envelope, you would have to, every 200 milliseconds, you calculate the power and you take You calculate it first 200, you calculate it over the 400, and you calculate it all the way to 2 seconds. So you calculate the delta power over these 2 seconds, say, and then you can cut off the last 200 milliseconds and give it as your feature. This is only because 0.5 hertz has a much longer period, right? It's 1 by 0.5, which is 2 seconds, and that's very long, and it's longer than our recording period. So we have to cut it in some way up for it to fit within these 200 millisecond windows. Now, the reason we have 200 millisecond windows, and this is something important to EMG as well, is that in order for the gesture decoder to make some response, in order for the gesture decoder to make a response, it needs that information over whatever window you've allotted it before it can make a decision, even, right? And so if we were to make it require 1 second of information, right? Calculate all these features over 1 second and then feed it. That means during real time, we would have to wait 1 second approximately before, like waiting for the participant's action before the gesture decoder would actually react. And so that's why we've kept it this small. Now, the processing steps that we do for each feature band, you can calculate the power envelope, maybe through the Hilbert transform, and then you log transform it, because what happens is when you take the power envelope, its distribution changes, and if you do the log transform, it comes back to normal again. This is some basic stuff. I think if you decide to study this area, this is a very basic thing that you come to. So I would not be too intimidated by it. And then for each signal across the trial, which means the session where we've recorded this one gesture, and it's separate for each gesture, right? So if the person did a different gesture, it's separate, like a separate trial. That's how we consider it. And
Rishabh,
yeah,
I'm going to guess that I speak for your audience by saying that these details of statistical analysis are beyond what we need. It's the overall concepts, which,
sure.
as I understand it, are you've got to decide how much time to give the system to make its
react to this.
decision in order to
Make this
minimize
decision.
the delay. And then you
Yeah.
apply fancy statistics in order
Sure.
to give it the best available data.
Sure.
How's that?
Yeah, that's mostly correct. Yeah, I think the main thing is that also whatever frequency you pick for the signal, like the different frequencies you pick, should be correlated with whatever activity you're trying to gauge. But that's mainly it. So I mean, that's a general idea, I think, as well.
Just a side note, Rishabh, if this is all published somewhere, I would be very interested in
Yeah,
looking at the
so this
details.
is on the sampling neural plasticity paper. I can always link it after for you guys to take a look at, but it is a
And
lot denser, so you'll have to take
no,
some time to read it.
it's my background, so I'm interested, but please keep going. John has
Yeah.
a good suggestion. Oh,
Okay.
the other quick question is, will you be sharing this paper, or is this not
Yeah,
possible at this
we
point?
can share this paper. This paper has been published already. It was published as of March. So
I'm sorry, I meant this PowerPoint, not the paper.
oh, this PowerPoint? Yeah, I can leave it for I can share this with Sarah if she wants to post it on the e-NABLE page or
Perfect.
something.
Okay.
Yeah.
Thank you.
So now this is our multi-layered perceptron decoder. So you have 256 channels. You've extracted 3 characteristics you want from each channel continuously. So you have 768 input dimensions. Okay, you can feed this through a multi-layered perceptron, and you'll have probably 7 nodes at the end for a prediction, like a probability for each of your gestures, and whichever has the highest probability for your model is going to be your predicted gesture. Now, for our case of decoding it to the arm, we still, as of now, we still take what is the most predicted over 1 second. So we take the mode prediction for over 1 second because it's just a smoother input for our robotic arm. We don't want too many gestures at once because it's a little bit harder for the participant to use. We train this model on a certain amount of days that we have, right? We split the rest so that the model sees what's true, what is it predicted, what is not, what is wrong. And so it can retrain itself. And then once it's done, we save the decoder weights, which is just the equation, right? And this takes a lot less hardware power than the training part of things. And so it's much easier to do real time. And then we test it for the day we're testing the device with the participant. Just a small thing here is that the reason we picked the gestures. So this is the delta band. This is the gamma band. We can see that the decoder weights are highest. It's just a simple thing of how we've picked these gestures as well. So yeah, if I don't know if you guys can see that, but that's the window at the bottom. But that's the idea. This is also published in the paper if you want to look. Okay, now towards the end, instead of translating the decoder inputs from our thing continuously, like every second, we take the predicted output for 1 second for the stability. And this is our simple, this is just our equation for basically the robotic arms movement. So that once the person does the action, it doesn't keep going to that direction. It slowly decays and it has some momentum and then it stops, right? Because you don't want it to be continuous. What if the person doesn't give it another input? So that's the idea. And then here's our small video of what we published on UCSF's press recently for our lab. So you guys can take a look. Yeah. So that's the work that we've done at the lab, and this is for one of our participants we've tested it with. I hope that was informative, guys. Now we've reached the end of the presentation, but that's what this work has amounted to for the decoding, and I hope that that has a decent overview of what the process is with signal decoding for this
Absolutely.
subject. Yeah. Do you guys have any questions?
I have a few.
Sure.
So I'll make it quick. So can you, just to step back, give us an overview of this lab? Looks really
Yes,
fascinating. I haven't
sure.
heard about it
So
before. Where you stand in your
yeah,
program, how
so
many
I'm
students?
mostly like a researcher. Like I'm like I guess I'm kind of Hongi's assistant in some sense, and my work specifically is towards the reliable signal decoding. So if someone has like a neural anomaly in their recording period, we can detect those and try to correct those so that the system becomes reliable for someone over time. Hongi usually works on the decoding as well as like the control of the smooth robotic arm. So like a lot of the control that we've just seen here, as a result of the lab's work over time. And we've been collecting this data since probably 2020, around there. And so it's taken a lot of development to bring it there. But I think yeah, if Hongi can also explain some of the details from his side if he'd like, but that's the main um, thing I would
And
say.
how big is the lab, and how many,
Oh, our
it's part
BCI,
of,
so Coronatia's total lab, uh, let me, I didn't think of this.
So
I would, yeah,
okay, Tim. So we have around like 20, 25 people, but we have three part of the lab. Some part doing rodent study, some part doing non-human primate study, and the part for the BCI study only have like, include Rishabh and the postdocs, like 5 people in total.
okay. And this is part of UCSF, this
Yes,
lab?
you're from
Uh,
UCSF. Yes.
It's great.
all
Um,
right.
so you're a young man, but you've been watching this field for about 5 years already. So, um,
Yeah.
Given the rate of change in all of these areas, when do you think there's going to be a system that I could ask a lot of questions here, but that e-NABLE volunteers could put together without understanding everything that goes into it, but being able to then, fabricate
Right.
and help customize for real recipients?
Okay. Well, listen. Okay, I think so. I think okay. Let's think about this. I would say realistically, with the muscle signals, I think it could be 5 to 6 years. I think if someone decided to take some initiative to develop that, I think 5 to 6 years is not out of the question. Like, because I think there are people who are far more talented in this community of making like feasible hardware and who have subjects like I saw, for example, the Elmo Dalio from Colombia, the Colombian e-NABLE, where they like tested it with amputees and they have a very good arm design based on the Kawaiwu. And so I think the hardware side, we have things covered. But, I think what would take some time is to make like a simpler system where someone could just, they perform some gestures with the arm for maybe the first 2 days. And every day that person woke up and used that arm, which is probably, mounted to them, they do maybe the first 1 or 2 gestures, right? And it recalibrates the entire system based off for that day, and it's ready to be used. I think the full end to end of that, I would say 5 to 6 years. But maybe this is a optimistic estimate. I'm unsure. But I would hope so. I think if someone took some initiative on it.
And what is it that's responsible for the fact? What's going to take 5 years for the hardware to get better, for the software to get better, for
I
one
wouldn't
person
say
like you to get good enough?
okay.
What goes
So
into
I
that?
don't think it's the hardware. I think we have the hardware already. I think the hardware is fine. The hard part about decoding, like in making that to like a basically like a feasible system for people to use, like almost what past first stage of FDA testing and whatnot, right? That's a lot of work in some ways, right? Like you have some type of medical device that you have to test, right? And
Well, yeah, okay, so let's take that out of the equation. The amazing thing is that e-NABLE does not have to go through the FDA testing side of
that's
things.
true. But like some heavy testing period, you're right. That's true. We don't have to go through the FDA. But I think, I mean, so I think the first thing that would take the longest, I think the hardware is already there, and I think someone could 3D print the arms and have some, like we see people who they have like the what's it called, OpenSCAD. They scale the arms based on the
Sure,
person's
sure. So
measurement.
let's take the
Yeah. So then
you're
the
saying
decoding
hardware. So
in
the
order
the
to
3D
work,
printed arm and
yeah,
servos,
yeah,
that's
um,
relatively under control.
right.
What's the
So one of the
what's
things
the
that would
bottleneck
be
right now?
it would be the sensors. Like if you saw recently, maybe you've heard about this. One thing that does interest me. So I right now use wet electrodes for the muscle segments, right? That's not that like convenient. And so like if you saw recently, not Elon, Mark
Meta.
Zuckerberg, Mark Zuckerberg had this video about him testing this like muscle armband that he had with EMG signals. It's a dry armband. I think something like that could be used to control the arm if it has good accuracy and it's been well tested. So something available like that would really help because you would have good signals as well as good performance for uh, just reliability and whatnot, and it's easy to charge. It's easy for the user. So I think integrating something like that would be really helpful. And then having a decoding system, which can be like developed maybe over the course of 2, 3 years, where you have this calibration. It's basically like an end-to-end device for someone.
Right.
That would be those two things are what really needs to be done. So yeah, that's
Okay.
what I would say.
So
Yeah.
so that bracelet that you're talking about from Meta
Yeah.
was developed in support of whatever the latest VR system is.
Right.
Um, but it's a very interesting bunch of hardware, and I imagine it's got a lot of computing power on board.
It has a little bit.
Do
Yeah.
we
Yeah.
do we know much about what it's actually doing and how it does it and how
Yeah.
well it does it?
So I actually, me and Holly were talking about this the other day. So there's this paper they published with 43 participants. And this is from Meta's labs in like New York, and they had the EMG, this band which they were testing, and so that was what it was based off of. And it does have the capability of running small things on it. But the main thing is that it ensures pretty reliable decoding. And if it's like a well-tested device across like a diverse population, maybe you wouldn't have to retune it and worry about these things for like a specific participant. So then it would be dependent on like the small computer maybe that can hold that model weights and then decode
Right.
and keep that simple. So if it's able to program and take some like maybe we have like a small computer which can like understand to take the
Right.
signal for this, recalibrate, and then just test, that would probably be the easiest within the arm.
So
That I see.
Rishabh, so I would encourage you to write to those people. Tell them
Okay.
about what you're doing.
Sure.
This would be a great story for Meta to be able to boast about. And their
Probably.
bracelet, I think, is useful for much more than what they've designed it for.
No, that's
They're
true. I
already
agree
going
with
through
that.
the economies of scale and the consumerizing and et cetera, et
Right.
cetera.
Yeah.
If you need any support in reaching out or getting the courage to reach out or whatever, but
Sure.
you're
All right.
plenty qualified
Right.
and
No,
you
that's a good
never know.
idea. Yeah. Yeah, I mean, we're also me and Hongi are obviously based in the Bay Area, so it's still somewhat feasible to do that. So at this point, that's something we should consider. Yeah. Um,
Yeah, I'll point out that we've had telephones for quite some time and we have email, and they're really easy to reach. The fact that you're on opposite sides of the country is
oh,
relatively.
which state are you from?
So I'm in upstate New York, not in New York
Oh,
City,
okay.
which is about 5-6 hour drive.
Right. Okay.
Listen, if you can get a rise out of them, and I'm putting you in the position because you're doing the work and you understand the
Sure.
technology in a way to talk to them, I would be delighted to go to New York and talk to them in person if they wanted to do that.
Okay. Yeah. All right. Thank you. I appreciate the help. We'll see. I do want to develop this into like a real time, like a full-on system later on. And I think it's something worth pursuing because I still think that simple solution doesn't exist yet, like end to end. So that's a good
Yeah,
idea you brought up. But yeah,
cool.
thanks. Yeah.
Okay.
So,
Anyone else have any
Rishabh,
questions?
so zooming into you, what are you're on a PhD program right now,
All right.
or
All right.
what's the
Here's where I have
latest?
the real kicker. Guess my age, guys. I'm
You're
17.
You're what?
17.
17. All
Okay.
right. So I didn't start with it because I thought, well, you know what? Are you guys going to listen to me for this entire presentation, considering my age? But I've been working in the lab with Hongi for maybe like 6-7 months now because I had initially started with this electric arm project on my own. And then I had kind of gone, I was like, this is like a really cool lab and you guys are doing stuff
Sure.
to the next level. So that's why I started to pursue it. But I think that that's just generally something I want to pursue down the line. So, yeah. I'm gonna probably go to
So,
bioengineering. So,
so you're in high school at
yeah,
this point.
right.
Oh, fantastic. That's great.
And when did you, where is e-NABLE in your life history?
So initially I used to like 3D print these like educational models for like this blind school when in India when I used to design it with Braille and stuff like anatomical ones. And then I was thinking like, we could probably use it for something more essential. Like people use my stuff, but at the same time, like I think there's still a lot of use that it has. And so I did kind of stumble upon e-NABLE like after there was like some I guess shoot, it's been a while. I'm thinking how I first saw it. But I remember like seeing kind of like there was this demonstration of like the e-NABLE Phoenix V3 hand that I'd seen on YouTube. I was like, okay, this seems pretty cool. And so I printed the first hand and I was like, okay, that's probably something I can do in the future. So like that's something like I can probably, get some help and I can start making those hands. So I started making mechanical hands and sending them to people. But I was like, okay, maybe we can take this to the next step. And so I started making this project. Maybe you said it like probably 8-9 months ago, and we kind of came here. So yeah, that's about it.
And
Very good.
Hongi, we only have 8 minutes, but Hongi, can you say something about your background? what are you involved in, and how does it all
Yeah,
fit in?
sure. So, my undergrad was at UW with the background in biology and philosophy, and I joined UCSF in 2022 for my PhD in bioengineering. It's a joint program between UCSF and Berkeley. So, I've been staying in lab for like almost 4 years. So I'm primarily working on like neural decodings, like Risha mentioned, and also doing some computer vision algorithm alongside with robotic control to assist BSET control. So that's pretty much what I'm doing right now. Yeah.
So you've been working with Rishabh on this
Yeah, I've been
program?
working
Is
with
that
Rishabh
right?
since summer this year, and he's doing a fantastic job.
Wow, awesome. That's great.
Okay. Well, and Hongyi, how old are you? Let's start there.
Oh, I'm 27. I'm pretty old, I guess.
There you go. Okay.
Yeah.
So, and you have a longer professional experience in this space, right?
Yes, I do. Yes.
Okay. Um, what do you think about reaching out to the Meta Lab saying we have an application that would be newsworthy and your hardware might be a major advance for?
Um, Why not? So that's what I'm thinking right now. Their commercial product is only $7.99. It's not too expensive to an extent. But I've been reading their papers. The hardware they're using on the paper and the one they're selling is two different products. So the one they're using in the lab is like there's much denser electrodes and
Mm,
much firmer, meaning like it can basically locate harder on your arm or wrist, so detect
mm,
much reliable signals. But the one that been commercialized is not that firm. So I mean, there's more noise penetrated through the system, and then they also somehow reliable on the computer vision side to track your fingers to help the control of the
that's very
decoder to
interesting.
extend.
Okay.
Yeah.
Uh-huh.
So, but still, it's a good product, I would say. I would try it definitely.
All
Because I'll
right
be
then.
also doing the same project in my undergrad, doing the it's like computer vision with it's like a cane for blind people, but with the depth sensors and
Understood.
one height and distance. Yeah.
Very good. Okay. Well, I'd encourage you guys to reach out and keep us posted.
All right.
Cool.
Yeah,
Yeah, thank you for that, the
if you
wise
could
advice.
if you could send Sarah your pitch and a
Yeah,
link to the
I'll
paper, that
email it to
would
her.
be fantastic.
Yeah.
Yeah, and this is great.
All right. Yeah. I
Thank
mean, you
you
guys post
for
this wherever. Yeah, I'm open to like I feel like this is really cool work. So, yeah.
Okay.
thank you
Well,
for taking the time, both of you.
Yeah.
Cool.
thank
Nice
you
seeing
all.
you.
Nice to see you again.
Thank you so much. This was such a great presentation. Thank you.
Yeah. You have a good one.
Bye-bye.
Bye-bye.
Bye.